All right, here we go. We need to go fast. You've done trig before. There's a lot of trig we have left to figure out. So some of this is reteaching from scratch. Some of this is just sharing a new perspective. What is a radian?
An angle in terms of pi.
An angle in terms of pi, but conceptually. That's good. Conceptually, what is it? It's a different way of measuring angles, yes, but conceptually, does anybody know what it is? Does anyone know how big it is, approximately?
A radian?
1 radian. How many degrees if you had to transfer?
7.
Well, so
90.
there's like
So you really don't have any clue what a radian is.
There's like 6 and a 7.
Wait. There's a 2 pi over 180 thing.
Oh, yeah.
Okay, do you remember the SOAR formula? I'm going to share with you conceptually what 1 radian is. Do you remember the SOAR formula? Okay. S stands for arc length. Theta is your measure in radians. And R is your radius. So if I solve for theta, that measure in radians, and I get that all by itself by dividing by R on both sides, there's theta. In order for that to be 1 radian, what has to be true about the arc length and the radius? They have to be the same. And there's your definition of 1 radian. So if I were to take an angle, there's my initial ray, and open it up, when this arc length here, S, is exactly equivalent to R, that's 1 radian. When I open an angle up, let's say, a little bit wider, okay, so that the arc length here is double the radius, that's 2 radians. Yes? And when I open it up triple, that's 3 radians. And then obviously you can go anywhere in between. Okay? For the sake of recalling, a 180 degree angle is how many radians?
3.14.
Pi. Very good. And there's your big conversion. That's the big method behind the conversion. 180 degrees is pi radians, aka 3.14. So when you open a circle and you take any semicircle, the length of that arc to the length of the radius is in a ratio of 3.14. It's an irrational number, but approximately 3.14 to 1. Okay? But the fact that 180 degrees is pi radians is the main reason for the way we translate from one measurement to the other, and we'll get there. This first example is just bringing that SOAR formula to life. So we have a SOAR formula, and they're telling us that a central angle is in a circle with radius 6. So your radius is 6. Intercepts an arc of length 15 inches. So what is the radian measure? So we're just solving for theta, dividing both sides by 6, and we get theta equals 2.5 radians. The radian measure is the ratio of the arc length to the radius. Okay? We lose sight often conceptually as to what this all means because we honestly don't use it often. There's rules that you guys have memorized, like converting from degrees to radians and converting from radians to degrees. Those rules are great because they're quicker, but they also make you lose sight of the conceptual meaning behind what a radian even is. Okay? Do you guys remember dimensional analysis? Okay. Dimensional analysis is the process of changing units. Okay? Changing miles per hour to feet per second or something like that. This is technically what you're doing here. We want to convert degrees into radians. So we're going to multiply this by 1 And multiplying by 1, as you know, does not change the value, but it's going to change the appearance because we're going to do it creatively. We want the degrees to cancel. So this is technically 30 degrees over 1. We're going to put 180 degrees on the bottom so that the degree and the degree will cancel. The equivalent to 180 degrees that we just talked about, but in another unit, is pi radians. So we multiply by pi radians. So our degrees cancel. The 30 over 180 reduces to 1 over 6. And we just end up with pi over 6 radians. Again, you probably don't think of that as dimensional analysis. You probably don't think of that as multiplying by 1. You just memorize the rule, which is fine, totally fine. But I just want to kind of remind you about the logic behind some of what we're doing so that you can better understand it. How many of you already knew that? 30 degrees pi over 6. That should be somewhat of a fluent transition already from last year, no? 30 degrees pi over 6. Okay, maybe not. We'll get there. You'll be there this year, I promise you. 90 degrees, same thing. Multiply by pi radians over 180 degrees. Again, your degrees cancel. Your 90, 180 simplifies to pi over 2. How about that? How many people knew that 90 degrees was pi over 2? Maybe a few more of you. And then negative 135, same thing, multiply by pi over 180. Your degrees cancel. Your 135 over 180, those are both divisible by 27, I think.
How'd you get that?
Oh, I did this once already. Well, I knew that they were all divisible by 5, so I did that first, and I got negative 27 pi over 36. And then both of the, oh no, they're all divisible by 45. That's easier to see, right? 45 goes into 135 and 45 goes into 180. If not, you do it piece by piece. Like I said, you definitely know they're all divisible by 5. Do that. Now 27 and 36 are all divisible by 9. And so if everything was divisible by 5 at first and then also was divisible by 9, I know originally it should have all been divided by 45. But I don't care if you simplify the fastest way or not. And then vice versa here we have radians. So it's currently in radians. We want the radians to cancel. So we're going to put the 1 radian, or pi radians on the denominator. And the 180 degrees up top. So your radians cancel. Oftentimes your pi's will cancel. And 180 divided by 3 is 60 degrees. Okay, jump to C. 1 radian. Multiply by 180 degrees over pi radians. So your radians cancel. And that's 180 divided by pi. Pi is a little bit more than 3. So that your answer should be somewhere around 60. It's actually 57 point, you need a calculator for this, 2958 degrees. It's going to be an irrational number because you're dividing by pi. But 1 radian is approximately 57 degrees. Any questions on that? Okay. So this next part, I'm going to go above and beyond what it says, but we're going to start with, obviously, A in the pi over 4 sequence. Okay? So this is 0. We know that. Do you know the equivalent of pi over 4 in degrees? 45. Okay. That's about the maximum amount of transitioning between radians and degrees that I'm going to want you to do. This is 1 pi over 4. I know it's weird to put the 1 there, but I'm going to put 1 pi over 4. And then this here is 2 pi over 4. Which normally we wouldn't see it written as 2 pi over 4 because, of course, it reduces. and it's going to coincide with pi over 2. But just hear me out. 1 pi over 4, 2 pi over 4, 3 pi over 4, and 4 pi over 4. So there's my half circle. There's my pi radians split into 4 pi pieces. Do you see them? Because my denominator was 4. So my half circle got split into 4 parts. And so then I can keep going, 4 pi over 4, which again, obviously 4 pi over 4 is not something you're going to really see, but it helps you place other angles. So you know 5 pi over 4 is just a tick past that. Then we have 6 pi over 4, which you're not going to hear about much because that reduces. 7 pi over 4. And 8 pi over 4, which of course is the same as 2 pi. Make sense? On the second one, 2 pi over 3. I'm going to start with 1 pi over 3. Then 2 pi over 3. Then 3 pi over 3. 4 pi over 3. 5 pi over 3. And 6 pi over 3. On each half circle, it got split into thirds. There are a total of 6 pieces here.
You have to memorize this.
It's just counting.
Yeah, but I'm confused. Why did you not have to break it up like you did the other one?
What do you mean break? So this one I had to split the half circle into fourths. So I have it in equal fourths. This one was in equal thirds because I was doing a third of pi, 2/3 of pi, and 3/3 of pi, aka the whole thing. Does that make sense?
Yeah.
Okay. Pi over 6, 1 pi over 6, 2 pi over 6, 3 pi over 6, 4 pi over 6, 5 pi over 6, 6 pi over 6. So there's my half circle pi being split into 6 wedges. Nick?
So did theta, alpha, and like beta all mean the same thing?
Yeah, we use Greek letters just to call, it's like the variable you call an angle. The thing about the pi over 6s, and we saw a little bit with the pi's over 4s, is that 2 pi over 6 you're almost never going to hear about because that reduces to pi over 3. 3 pi over 6 you're not going to hear about, reduces to pi over 2. 4 pi over 6 reduces to 2 pi over 3. Here's the thing. Does anybody know the reference angle that goes along with pi over 4? Anything pi over 4? 21 pi over 4? 37 pi over 4? They all have the same reference angle. 45 degrees, very good. Anything that, once it's reduced, anything that has a divided by 4 is a reference angle of 45 degrees. Because pi is just 180 degrees. 180 degrees divided into 4, 45. Anything with a denominator of 3, 60, because pi over 3 is 180 over 3 is 60. So if someone asks you for 101 pi over 3, you don't have to worry about really coming up and transitioning that. It's a denominator of 3. It's a 60-degree reference angle. And anything with a 6. Now, when I say anything with a 6, I'm not talking about 2 pi over 6. Because it's once it's reduced. And 2 pi over 6 would reduce to pi over 3. And that is a 60-degree reference angle. But any of these pi over 6, 5 pi over 6, 7 pi over 6, 11 pi over 6, that's all 30. And then anything with a reference, with a denominator of 2 on part D is a 90-degree reference. Okay? Coterminals. Okay, coterminal angles, you know what they are. You did them last year. However, I'm going to tell you this. If they're in degrees, you keep them in degrees. If they're in radians, you keep them in radians. And it's finding, in this case, a positive angle less than 360, if you're talking about the degrees, or less than 2 pi if you're talking about the radians. That's going to be a coterminal. Now, coterminal angles, if you just look at the visual, like if we give this, we say what's a coterminal to this angle, that just is resulted from swinging the ray around one full circle, which in the case of degrees is swinging it around 360 degrees, or some multiple of 360 degrees. In radians, it's some multiple of 2 pi. So when you're coming up with coterminals, you're adding or subtracting multiples of 360 degrees or multiples of 2 pi. So for this 420, which is too big, we're going to subtract 360, and you get a 60 degree is the coterminal between 0 and 360. Negative 120 is too small. We're going to add 360 onto that, and we get 240 degrees as our coterminal. 750 is way too big, way too big. We have to subtract 360 twice. So kind of ringing your terminal ray around the circle 2 times backwards. So 750 minus 720 is 30 degrees. It's going to be tougher in radians for you guys because you're not used to thinking in radians. First of all, D is 17 pi over 6. But in order to add and subtract 2 pi, we would need a common denominator. And our denominator is already 6. So how many pi's over 6 is equivalent to 2 full pi? 12. So for the 17 pi over 6, we're going to subtract multiples of 12 pi over 6, which we only have to do once. Subtract 12 pi over 6, and that leaves you with coterminal 5 pi over 6. How about pi over 12? How many pi's over 12 is the equivalent of 2 pi? 24 pi over 12. So we're going to add on 24 pi over 12, and we get 23 pi over 12. And here we have 6 again, so that's 12 pi over 6. We need to add multiples of 12 pi over 6. Adding 12 pi over 6 is not going to be enough. We're going to have to add 12 pi over 6 twice, which is really going to be adding 24 pi over 6. And that's going to leave us with 7 pi over 6. So we're not going to get to the bottom. Maybe we'll pick up with that tomorrow, that linear speed, angular speed. So any homework questions on linear speed or angular speed? Skip. Okay, this is just the SOAR formula again that we already talked about. Can you hold on 1 second? With the SOAR formula, the only thing I want to reiterate is that the theta is the measure of the angle, has to be in radians. So that problem has 120 degrees at the central angle. You need to make that radians first before you can use it. Yes? Okay.